We are now ready to discuss Theorem 6.10, the conditional strong AEP. For any sequence X which is delta typical, define the conditional typical set T y given X delta sub n of the sequence X to be the set of all typical Y's such that the pair XY is jointly delta typical. If the size of the conditional typical set is at least equal to 1, that is, there exists at least one typical Y such that XY are jointly typical, then the size of the conditional typical set is lower bounded by 2 to the power n times entropy of Y given X minus nu, and upper bounded by 2 to the power n times entropy of Y given X plus nu, where nu tends to 0, as n tends to infinity and delta tends to 0. Here are some remarks. Consider dividing the size of the jointly typical set Txy by the size of the typical set Tx, which is approximately equal to 2 to the power n times the entropy of x and y divided by 2 to the power n times the entropy of x. This is equal to 2 to the power n times the entropy of xy minus entropy of x. And this is equal to 2 to the power n times entropy of y given x. In other words, the number of typical y sequences that are jointly typical with a typical x sequences is approximately equal to 2 to the power n times the entropy of y given x on the average. Theorem 6.10, that is the conditional strong AEP, guarantees that this is so for each typical X sequence as long as there exists at least one Y sequence that is jointly typical with that X sequence. We will divide the proof of Theorem 6.10 into two parts. First, we prove the upper bound on the conditional typical set. It says that if the size of the conditional typical set for a particular typical X sequence is at least equal to 1, then the size of the conditional typical set is upper bounded by 2 to the power n times entropy of Y given X plus nu, where nu tends to 0 as n tends to infinity and delta tends to 0. For any nu greater than 0, but a strong AEP, consider 2 to the power minus n times entropy of x minus nu over 2 greater than or equal to the probability of the x sequence, where this probability is equal to the sum of pxy over all y sequences. This is lower bounded by summing pxy over all y sequences, which is delta typical with that typical x sequence. Now we have x and y being jointly typical, so by the strong joint AEP, pxy is lower bounded by 2 to the power minus n times the entropy of x and y plus nu over 2. This lower bound is valid when delta is sufficiently small. Since this lower bound does not depend on the sequence y, this is simply equal to the size of the conditional typical set times 2 to the power minus n times entropy of xy plus nu over 2. The remaining steps are very similar to the proof of the upper bound on the typical set Tx in Theorem 6.2, that is the strong AEP. First, we move 2 to the power minus n times entropy of xy plus nu over 2 to the other side of the inequality. Then we get the size of the conditional typical set for that particular sequence x, upper bounded by 2 to the power minus n times the entropy of x minus nu over 2 plus n times entropy of xy plus nu over 2. This is equal to 2 to the power n times entropy of xy minus entropy of x plus nu. Now entropy of xy minus entropy of x is simply conditional entropy of y given x. So we get the size of the conditional typical set is at most equal to 2 to the power n times entropy of y given x plus nu. The formal proof of the lower bound in Theorem 6.10 is given in the textbook, which has a lot of fine details. Here we give an outline of the proof by means of a very simple example. Let the alphabet x be 0, 1, and the alphabet y be a, b, and c. Consider a particular pair of jointly typical sequences x and y as shown. For the x sequence, all the zeros occurs first, and then all the ones. For the components of the y sequence corresponding to x sub k equals 0, all the a's occurs first, then all the b's, and then all the c's. Same for the components of the y sequence corresponding to x sub k equals 1. There are approximately n times p0a pairs of 0a, approximately n times p0b pairs of 0b, approximately n times p0c pairs of 0c, approximately n times p1a pairs of 1a, approximately n times p1b pairs of 1b's, and approximately n times p1c pairs of 1c's. Now observe that by rearranging the components of y corresponding to x sub k equals 0, the joint typicality of the pair of sequences is preserved because there are still approximately n times p0a pairs of 0a's, n times p0b pairs of 0b's, and n times p0c pairs of 0c's. Likewise, by rearranging the components of y corresponding to xk equals 1, the joint typicality of the pair of sequences is also preserved. Now the number of possible arrangements is equal to the product of two multinomial coefficients. The first one being np0, np0a, np0b, np0c. The second one being np1, np1a, np1b, and np1c. Using our approximation for the multinomial coefficient, for the first one, we get 2 to the power n times p0 multiplied by the entropy of the conditional distribution of y given x is equal to 0. For the second one, it is approximated by 2 to the power n times p1 times the entropy of the conditional distribution of y given x is equal to 1. Now the entropy of the conditional distribution of y given x is equal to 0 is simply the conditional entropy of the random variable y given the random variable x is equal to 0. Likewise, the entropy of the conditional distribution of y given x is equal to 1 is simply equal to the conditional entropy of y given x is equal to 1. And this is equal to 2 to the power n times the conditional entropy of y given x. In other words, for any particular pair of jointly typical sequences, we can generate approximately 2 to the power n times entropy of y given x pairs of jointly typical sequences. Therefore, for a typical sequence x, as long as there exists a typical sequence y which is jointly typical with that sequence x, the total number of typical y sequences jointly typical with that x sequence is at least equal to 2 to the power n times the entropy of y given x minus nu, when nu is a small quantity that goes to 0, as n tends to infinity and delta tends to 0. So we have established theorem 6.10, the conditional strong AEP. Here is an illustration of the conditional strong AEP. On the top is the delta typical set T sub x, and at the bottom is the delta typical set T sub y. For each delta typical x sequence, as long as there exists another y sequence which is delta typical with it, then there are approximately 2 to the power n times entropy of y given x such y sequences. Likewise, for a delta typical y sequence, as long as there exists one typical x sequence which is delta typical with that y sequence, then there exists approximately 2 to the power n times entropy of x given y such x sequences. The next result is a corollary of theorem 6.10. For a joint distribution Pxy on alphabet x times alphabet y, let S sub x delta sub n be the set of all delta typical x sequences such that the conditional typical set Ty given x delta sub n for that particular x sequence is non-empty. In other words, the set S sub x delta sub n is the set of all delta typical x sequences such that there exists at least one y sequence which is delta typical with that x sequence. Then the size of the set S sub x delta sub n is at least 1 minus delta times 2 to the power n times entropy minus psi, where psi tends to 0 as n tends to infinity and delta tends to 0. Basically, this corollary says the following. Although the set S sub x is a subset of the typical set T sub x, the size of the typical set T sub x and the size of the set S sub x grow at the same asymptotic rate. The next proposition says that with respect to a joint distribution Pxy on x alphabet times y alphabet, for any delta greater than 0, the probability that the random sequence x being in S sub x delta sub n is greater than 1 minus delta, for n sufficiently large. This proposition says that with very high probability, we can obtain an x sequence such that there exists a y sequence that is jointly typical with that x sequence. The proof of proposition 6.13 is straightforward, so it is omitted here. From these two results, we see that the set S sub x and the set T sub x have almost the same asymptotic properties. We now prove corollary 6.12. By the consistency of strong typicality, if the pair of sequences x and y are jointly delta typical, then x is delta typical with respect to the marginal px. In particular, x is in S sub x delta sub n because there exists at least one y that is jointly typical with that x. Now we write the jointly typical set Txy as the union over all x sequence in S sub x of all xy pairs such that y is jointly typical with x. Using the lower bound on the size of the jointly typical set Txy and the upper bound on the size of the conditional typical set Ty given x, we have the size of the jointly typical set Txy lower bounded by 1 minus delta times 2 to the power n times the joint entropy of x and y minus delta, and upper bounded by the size of the set S sub x delta sub n times 2 to the power n times the entropy of y given x plus nu. From the lower bound and the upper bound, we obtain the size of the set S sub x delta sub n greater than or equal to 1 minus delta times 2 to the power n times the joint entropy of x and y minus the conditional entropy of y given x minus lambda plus nu. Since the joint entropy of x and y minus entropy of y given x is equal to the entropy of x, this is equal to 1 minus delta times 2 to the power n times the entropy of x minus delta plus nu. Then the theorem is proved upon letting psi equals lambda plus nu. We now show that strong typicality exhibits a very special structure called the asymptotic quasi-uniform structure. For two jointly distributed random variable x and y, consider the two-dimensional strongly joint typicality array, whose rows are labeled by the approximately 2 to the power n times entropy of x typical x sequences. The columns are labeled by the approximately 2 to the power n times entropy of y typical y sequences. For each particular typical x and a particular typical y, if the xy pair is jointly typical, then we put a dot at that entry. By the strong joint AEP, the total number of dots in the array is approximately equal to 2 to the power n times the joint entropy of x and y. If we fix a typical x sequence, by the conditional strong AEP, the total number of dots is approximately equal to 2 to the power n times the entropy of y given x. In other words, every row in a strongly joint typicality array has approximately the same number of dots. Likewise, for a fixed typical y sequence, the total number of dots is approximately equal to 2 to the power n times the entropy of x given y. Again, each column of the array has approximately the same number of dots. Now we look at a three-dimensional strongly joint typicality array. In this array, there are approximately 2 to the power n times the entropy of x typical x sequences, approximately 2 to the power n times entropy of y typical y sequences, and approximately 2 to the power n times entropy of z typical z sequences. On the plane corresponding to a typical z sequence, z0, if there is one dot on the plane, then there are approximately the same number of dots on each plane parallel to that plane. Likewise, for a fixed typical x0, y0 pair, for the cylinder corresponding to that pair, if there is one dot in the cylinder, then there are approximately the same number of dots in each cylinder in the same direction.